Hello? Okay, I think it's about time to start. So yeah, today we'll finish purification, and if extra time, we'll talk a little bit about classical computation. Okay. Oh, forgot to open this. Hello. Okay, and yeah. So last time we start with this thing about entangled pure state. So we see that the entangled pure state always have this streamy decomposition. So in form is this. So we have system A, B. So some system A and system B, and we think about we have a pure state that that is over both of the system, and so this state may be entangled, and so we got this. This state might be entangled, but we see that this entangled state can always be written as this form. Psi equal to sum over I lambda I and IA and IB. And as we say, the important thing here is here the I are summing over the same index. So you increase I from 0, 1, 2, 3, and IA from 0, 1, 2, 3 on A, and IB is also 0, 1, 2, 3 from IB. And here these lambda i's are non-negative real numbers, and IA and IB are also normal bases. Yeah. And yeah, so this is quite special. Quite special because here we don't even assume A and B have same dimension. I guess I didn't stress this, but A and B can have different dimension. Maybe one of them is larger, and so really also normal bases should have different elements, but you still have streamy decomposition here, and that's because some of the lambda I can be 0. And we kind of see this from the proof here. So the proof of streaming decomposition is you just write your entangled state in arbitrary decomposition and do SVD, and you see that the number of a singular value can be only as much as the smaller of m or n, and where m is the dimension of m is the dimension of system A and n is dimension of system B. Okay. So you have, say here, m is smaller, so you have n of the singular values, and then you have a whole bunch of 0, etc. Okay. Okay, and yeah, so we have a whole bunch of names, and just from the discussion before, we see the terminology here is a bit weird. We have IA and IB. Okay, so IA and B are Schmidt bases, and so as we said last time, here everything is a bit confusing because whether you want to include lambda equals 0, because in this equation, the summation lambda I, IB, you can have if lambda is 0, you can just not write it. Okay, but if you want I and IB to be 4 bases, then it's a bit tricky of how you define I and IB. But anyway, so those are edge cases, and in general, people call them streaming bases. And those lambda are called Schmidt coefficients. And now there is a Schmidt number, which is pretty well defined. Is the number of non-zero lambda I. But also, if you don't even include lambda I equal to 0 as a Schmidt coefficient, then you are just the number of lambda I. Okay. And anyway, so it's a bit confusing on the terminology, but go back to how is Schmidt decomposition related to entanglement. So basically, this Schmidt coefficient, this set of number Schmidt coefficient here, will be related to how your state are entangled. How your state is entangled. Okay. And I guess there are two things. So first thing is that we want to say that Schmidt coefficient is some property that's global between A and B. Okay, so that's why it's probably a property on entanglement instead of just something that you can change locally. And to see this, you see that if you do some local transformation on your state, so if your state has streaming decomposition is summation I, lambda I, IB, and you do some unitary that act on A alone, then your streaming decomposition will become this some I lambda I and U on IA and IB. And you see that unitary transformation on IA give you another orthonormal basis. So this is also a Schmidt decomposition. So you see that you go from a Schmidt decomposition and you apply a unitary on local part, then immediately you get another Schmidt decomposition. And the important thing here is that you see these two Schmidt decomposition has the same lambda I. They have the same set of lambda I here. Okay. So yeah, so from here, this line here, we very quickly see that the Schmidt coefficient is preserved on the unitary transformation on local subsystem. So you do any UA, any UB on those subsystems, the Schmidt coefficient doesn't change. And the Schmidt coefficient really is about the global property of the state. And then the next thing I want to say is, I guess we should say this first. And you can show that if your Schmidt coefficient is only one of them is 1 and all other is 0, and that's if only if your state is a product state. Okay, so as we say very quickly last time, one of the direction is easy. So if you go from this to this, it's very easy because you only have one of them, then you are just have 0A tensor 0B, and obviously that's a product state. And the other way around, you need to work harder, but you can show that if you are, I guess, you want to show your product state and Schmidt decomposition only has a coefficient O equal to 1. Yeah, I guess you need to here kind of assume that the Schmidt decomposition is unique, and more. I guess we didn't assume the decomposition is not unique. But to say this, basically we already assume that the coefficients are unique. So the streaming coefficient for every state is unique. Okay, is unique, and so we can say this statement. Okay, and so this is the easiest case to use the streaming coefficient to say whether your state is entangled or not. So this is a very strict case. And in more general, we can feel that if your streaming coefficients are more spread out, then your states are more entangled. And for example, if you have like every one of the coefficients are equal, then usually that means your state is maximally entangled between A and B. Okay, and yeah, but we don't go into detail here. There are many ways to describe entanglement between two states, and but it usually requires you to calculate some function on those streaming coefficients. Okay. And yeah, if you want to study this, I think this is in chapter 7 of the book. It will talk about entropy of your system, etc. Okay, similarly there are some information theory. Okay, so that's streaming decomposition. And here we have a bit of streaming coefficient. Okay, so yeah, so also, I guess I forgot one thing. So if your streaming coefficient is this distribution, then obviously your streaming number is equal to 1, because only this 1 is non-zero and all other coefficients are 0. So number of non-zero coefficient is 1 here. Okay, and we have a bit of inequality that is always satisfied by the streaming number. Okay. So the streaming number, as we said before, is the number of streaming coefficient that's not 0, and obviously, yeah, because your lambda psi is this summation lambda I b, and so the number of non-zero coefficient cannot be more than I guess here this is a bit tricky. Okay, this is a bit tricky in how I define this set, so I guess let's skip the middle part. Really what we want is, we want to say this is less than equal to. Okay, so let's ignore the middle part, because how you define a set of I and IB is a bit weird. Okay, but anyway, so and it will be less than equal to, there will be less equal to the dimension of dimension of system A, and also less than equal to a dimension of system B, okay, because just because kind of because of the thing we crossed out, because you cannot find. I guess here I'm confusing myself. So we are thinking. No, it's very weird. Okay, so yeah, let's ignore the middle part for now. Okay, and yeah, yeah. Anyway, so from the SVD, we kind of see that the non-zero coefficients cannot be more than the smaller of the dimension A and or dimension B, and the non-zero coefficients is less than this dimension here. Okay. And so far is a bit review on streaming decomposition. Any question? Otherwise, we can go over some example here. And yeah, I guess this time. Anyway, yeah, let's try to see streaming decomposition with a bit of easy examples. So we have those 3 two-party states, and we want to see what are their streaming decomposition. And we have 1 over square root 2, 0, 0, plus 1, 1, and 1 over square root 2 plus 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 minus minus, and then it's plus plus state. And yeah, what are their streaming decomposition? And actually they are all already in streaming decomposition kind of. Okay. And the first one is obviously in streaming decomposition. We have, you can just multiply this 1 over square root 2 inside, and then you have the two streaming coefficients being 1 over square root 2, 1 over square root 2. And you have our IA is 0, 1, and IB is 0, 1. Okay. And what about the second one? Second one is also kind of already in streaming decomposition. So you think IA is a plus minus, and IB is plus minus. So this is already in streaming decomposition. But then here we see that the streaming decomposition is actually not unique. So this state is actually equal to this state. So if you calculate is this thing in 0, 1 basis, then you have that. So you have this plus and the minus go into 0 and 1. Then you see that the cross term cancel in the middle. So the plus it become is 0, 1 plus 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And this minus becomes 0, 0 minus 0, 1 minus 1, 0 plus 1, 1. And so the middle part cancels out, and you see that this state actually equal to 0, 0 plus 1, 1. Okay. So yeah, this is some cool thing about this EPR pair. EPR pair can be written in any basis. And I think this is I forgot. I think we also do this in homework, something very similar, where we say EPR pair you can rotate in any basis, and yeah, you can rotate the first and the second qubit with a different unitary, and will stay an EPR pair. Okay, and anyway, so those two things. So this thing actually we see that those two states are actually a two state. Are actually a same state, and yeah, they have the same streaming coefficient. So we see our streaming coefficient, they have a degeneracy. They are both 1 over square root 2, and and then because of this degeneracy, we can pick the direction of this basis quite arbitrarily here. Okay. And the streaming number for those two examples is 2. Okay. And yeah, then next example we have this plus state, and this is already written in streaming decomposition. We have just lambda I equal to 1, and IA where IA equal to plus and IB equal to plus. Okay, so both IA are 0, so lambda 0 equal to 1, then 0A equal to plus, and 0B equal to plus. Okay, and I guess so this is already in streaming decomposition form, but we want to say that streaming decomposition is here is useful to show that this state is a pure state, because you can think about if you are given this form, so if you are given this state in computational basis, then it's less clear whether this state is a product state. Okay. So if it's in computational basis, then you are given is 1 over square root 2, 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And so you see this has a double turn, and it's not obvious whether this state is entangled or not. Maybe it's obvious to you, but it looks a bit complicated to me. Yeah. So it has a lot of turn here, and if you want to check a state with this kind of form where they are entangled, then you can do streaming decomposition. So basically, you want to do the SVD of its coefficients, then you will get is equal to this form. For this state, the streaming decomposition is actually unique, and yeah, you get it to this form, and you see the streaming number is 1, and then you know the state is not entangled. Okay. So yeah, so this is about streaming decomposition. Any question? Yeah. I guess another thing I want to say a little more here is a bit criticized about the way we do this. So yeah, so a bit of criticism on this using streaming number to determine the entanglement of your quantum state is that this measure is not robust. Okay, so we only count the streaming number whether equal to 1 or not. But you see that the streaming number is something very sensitive on streaming coefficient. So for example, you have this thing is so you have this kind of state is has streaming number 1. Okay, so but if you have something that's very you can have some distribution of streaming coefficient that's very close to 1000. So maybe you have 0.99 and 0.01 on every other thing. Okay? And intuitively, the distribution is very close to this 1000 distribution. But if you count the streaming number, and it will be huge. Okay? So maybe your distribution is 0.9 and 0.01, and there are 10 of them. Okay, 0.01. Okay, and you count streaming number. This is maximum. The streaming number is 11, and but intuitively you think this thing should have a small, not too much entanglement, because this distribution looks very like this distribution. Okay, and yeah, that's why we have in more advanced theory we have a way to calculate entanglement that is more more smooth function on your streaming coefficients. Okay. Yeah. So that's something you can look up. And well, okay. So let's go to the next topic. So let's talk about purification. Okay. And purification is now finally go back to something related to reduced density matrix. So purification intuitively is something you want to do. That's reversing of taking a partial trace. Okay. And yeah, and so in more detail, this is what we do. So we are given some row A on system A. Okay. And so we start, I guess I should write row A here. So we have some row A, and so we want to find we have a weird notation here, but anyway, then we want to find some entangled pure state AR such that if you do partial trace on AR, it becomes your row A. Okay, so when we will partial trace, we were given a two-body state, and we get a one-body density matrix. And now we want to do the inverse operation. We have a one-body density matrix, and we want to say, is there a two-body state AR that gives you this density matrix? But if you want to just get a two-body density matrix, that's too easy. You can just have a row A tensor whatever thing on row A tensor whatever row R here, and you partial trace, you get back to row A. And so make the procedure harder and more useful, we require that our AR state is a pure state. Okay, then it's harder. Okay, so we want a pure state where you do partial trace, you get back to your mixed state here. Okay, row A. And here, I guess, yeah, in this course we think this as only a mathematical procedure, and this is usually what happens, but I just read recently that there are also papers that try to do this as an actual physical process, that when you have multiple copy and overall, and yeah, actual algorithm, just a few notes here, okay? And yeah, so you have many copy of row A. You can try to do this in actual physical process, but generally that's very hard. You need a lot of copy, and you only get approximation. Yeah. So for now, in this course we treat this as only a mathematical procedure. So we think that mathematically, if we get this number, this row A here, so we have full description of row A, and how do we get a full description of some pure state AR here? Okay, and okay, and in fact, the thing here is, what should I say? In fact, that this process, even how to calculate it is not very important. The most important thing to know here is that this process can be done. Okay, so it's very useful to know that. I guess we go over a bit of theorem. So the theorem we want The theorem that's very useful is that every density matrix row can be purified. Okay, so you give any matrix, density matrix on any system row, any system A. So you give this row A, you can always find the R and the state AR, such that row A equal to trace AR. Okay. And it's very useful, mostly because we don't like density matrices. Okay. Because density matrix, the n square element instead of n element if you are in n dimensional. And yeah, density matrix are just very hard to write. And a lot of time you like a pure state. Okay. And with this purification, a lot of time you can think about if I don't want to do something on density matrix, how about I think about just doing something on if I think I just have a bigger system and I have a pure state AR. Okay. And that will make a lot of derivation a lot easier. Okay. And anyway, so that's purification, and as we say, it's a reverse of partial trace. Okay. And yeah, then let's now actually prove this a very useful theorem. So we want to prove that any density matrix row can be purified. Means that you can always find this AR. Okay. And we give a very constructive proof. We just told you how to calculate the purification of a row. Okay. And well, we know rho is a PSD matrix, so you can write it in eigenbasis this eigenbasis decomposition. You have the eigenbasis as orthonormal. And we actually don't need the orthonormal, we just need whatever decomposition here. Okay, so rho A equal to this sum I pi and projected onto IA. Okay. And yeah, then we just say our purification is just this state. So AR is summation I, so pi square root pi, where pi is this pi here. There are probabilities, so you can take the square root, and then IA from this IA, and just so pi and IA come from the top, and then we write this in. So you see that we write this in streaming decomposition. Okay. So we just put whatever IR here, where IR is just whatever orthonormal basis on the system R. Okay, and yeah, so this is kind of already a proof, but we just need to do a bit of check. So we have this construction here, and we want to check that you partial trace R, it actually give you back a row A. Okay. And yeah, so let's do calculation, partial trace R, AR, and then as you see, writing down density matrix is hard because now it's a one index, because we already have also have the broad vector, we need to sum over two indices. So I have a sum I, sum j, and I is the index for ket, and j is the index for broad. Okay, so j, jr. And then we do partial trace, so we trace over, and the partial trace is linear, so it's just a summation over everything, and then you partial trace on the R part, so trace over this IR, JR. Then we use the IR and this IR, JR are also normal basis, so we do trace, this is just delta IJ, and then finally you can get rid of this delta ij with summation j, where you put this j equal to I. And I think I have a typo here, sorry. So this should not be j broad, so this should be wait, let me think. So it's wait, I think the typo is the R1. Okay, so this one is actually correct, and the wrong one is here. Okay, so this should be this is a very confusing, so I'm mixing up a lot of things here. So this should be IA and IA ket and IA broad, and then this whole thing equal to rho A. Okay, sorry for the hip up. Hip up here, and yeah, so anyway, we check that you do partial trace on R, you actually get back to row A. Okay. And yeah. And hopefully this also let you see that this while Schmidt decomposition is very useful because you get a row A here. You can quickly write down a Schmidt decomposition of the two-body state AR, and then from Schmidt decomposition, it's easy to calculate its it's also easy to calculate its component on A. Okay. Sorry, it's a reduced density matrix on A. Okay. And yeah, so that's purification. It can be done mathematically, and it's very important to remember that purification exists. I guess something we can say a little more. Do we have to say here? I guess here we can say a little thing here is that purification is not unique. Purification. Kind of obvious from here, and just from here we see that we can just pick arbitrary different IR here, then we'll get a different purification. So you have the same reduced density matrix. There are many different purification. Okay. And yeah. So that's about the purification procedure. And so that's so picking different IR is just one way to give a different purification, but actually you can also pick a different decomposition here to get a different purification. So there are many ways you can do purification. So as you see here, so here if IA are also normal, you get a Schmidt decomposition, but you can get so if you just see the checking here, you only need the IR to be also normal here. So you can even pick a decomposition where IA is not also normal, and you still get a purification. Okay, so yeah, that's a purification. Yeah. Anyway, and then we have we have actually two more slides. I forgot this one. But anyway, so the second last slide we have this picture that try to get a summary of the thing we talk about. So we have this purification, Schmidt decomposition, and partial trace, and so the relationship kind of like this. So we have an entangled pure state AR, then we take a partial trace of R, partial trace on R, then we'll get a density matrix, reduced density matrix. This density matrix is rho A. And then we will do purification. We will get going back to entangled pure state AR. Okay? And they are a bit different. So partial trace is something actually you can do kind of physically. You just throw out your R register, then you will get your reduced density matrix, because we know reduced density matrix actually is just this state that this state on only the A part. Okay, so this is quite easy to do, but for purification, so if you get lost of your R, then it's very hard to grow your R back. Okay, so if you are just give a reduced density matrix right away, then it's very hard to physically. I think it's almost I think if I just given one copy, then it's impossible to just purify back to get the AR. Okay, so physically they are very different, but mathematically you can go this way and go this way. Yeah. And here I should say this is reduced parenthesis. Okay, and yeah, we also see that the form of okay, now we go to a bit of Schmidt decomposition. So we see that the form of this entangled pure state, we can write it in this, always write it in the Schmidt decomposition. So AR equal to sum I and square root PI IAIR. And this will correspond to rho A being this summation I PI IAI. Okay. So we see the Schmidt coefficient here, Schmidt decomposition here actually correspond to the eigenvalue decomposition of rho A. Okay. So if all those P are different, those IA will be eigenvectors of rho A, and this IA will also be the same IA here. Okay. And Schmidt coefficients are those square root Pi, and Pi, as we say, are the eigenvalues of rho A. And then also, if you think rho A as the ensemble over these eigenvectors IA, then this Pi will be probabilities of IA. And when we have the square root Pi equal to only one of them being 1 and the other equal to 0, we think AI is a product state. And that's also when, so if AI is a product state, that will also mean rho A is a pure state. Okay. So this is square root Pi equal to 1000 also means Pi equal to 1000. And otherwise, AI is an entangled state and rho A is a mixed state. Okay. So this is a summary of everything about Schmidt decomposition and purification. Okay. And the next part, about mixed state is we want to say something on Bloch sphere. And so mixed state can also be marked on Bloch sphere. So we kind of go back quite a few slides back to when we talk about this Bloch sphere is representing 1 qubit. And we say, so a bit of review, we say this x, y, z axis correspond to sigma x, sigma y, sigma z in a whole bunch of different ways. And also the most important thing on Bloch sphere is each point on Bloch sphere means one pure state of 1 qubit pure state. And actually this is correspondence is even stronger. So if you think about something not on the sphere of the ball, so we think about something inside the ball, actually every point inside the ball corresponding to a mixed state of 1 qubit. Okay. And and then we have a very nice geometry property here, which we will not prove, but it's very useful in all sort of the derivation you do. That is, so geometry here actually corresponds to something. So the coordinate the coordinate of the mixed state is how do I say? So you think about mixed state as a linear combination of pure state, then the coordinate will also be the linear combination of the corresponding coordinates. So I guess it's easier to see an example. Okay. So we have this origin here. So this is 0, 0, 0, and so on this ball, the 0, 0, 0 is the average of this 0 vector and this 1 vector, right? So this origin point is 1/2 of the north pole plus 1/2 of the south pole, and this also and so its density matrix actually also correspond to the summation of this density matrix plus this density matrix divided by 2. So yeah, so the origin 0, 0, 0 and corresponding to this totally mixed state density matrix, and so it's equal to, we know it's 1/2 0, 0 plus 1/2 1, 1. Yeah. And we also know is 1/2 plus 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 1/2 minus minus minus, and we see that in terms of geometry on the ball, it also check out. So because you take this 1, 0, 0 point and this minus 1, 0, 0 point, and you average them, then you become this 0, 0, 0 point. Okay. And and so here this is kind of well, it's a proof with a very high technique, but we'll kind of prove that the totally mixed state, which correspond to the middle point, this origin point, is 1/2 of every different endpoint of any lines here. So you can just take any direction, and so you can take any direction on the sphere, and you add those two things together, and you give a middle point. And I should draw a straight line better. Okay, let's try to draw a straight line better. So take any direction, and you average those 2 points. So those 2 points on the sphere, they are pure state, and the average that you will become the middle point. And so you know average over this state plus this state also always become the totally mixed state. Okay. And yeah, but this geometric property here don't just work for the middle point. It works for every point inside the ball. And you can even have the average of 2 mixed states, and then the average of several mixed states, and the same property will hold. Okay. So it's some nice thing to know. Okay. And we still have 10 minutes until break, but I guess any question, or we can start on classical computation now. Or let's see. Should we? Let's try to have a break here and start early next class. So let's try to start on 4:20. Okay. Okay. So let's take a 10-minute break and come back at 4:20.这个是都是在 matrix。OK， 这些可以。有没有我们没证过的东西啊？我不知道，看一下。算了，不要乱动，这很容易当掉。
我印象
没有。
就是基本上就是把，这个应该就是把刚刚那个 SVD 的证明过程。
是哪一个？这个是。
稍微套一下就。
That's the 这个是刚才说的那个 if only if。
对。
OK。
然后
我都不记有这一题了。OK。
然后这个
为什么？为什么是 won't count 的？
没有，我还没改。
这你还没改？
这应该也可以算。
对啊，这就算一算。
然后现在这个我其实我还没有看这个数字到底是不是对的。我确认。
因为那个是很奇怪，这是都波手跟都在鬼数字，你要去算一下。OK。我看一下有没有需要算的东西，看起来好像没有。那同学有问题吗？
我可能要问你，然后你可能不方便回答，可以先手册。
没关系，你可以先问。
然后就是因为上次电视听那时候开始听太懂，就是这个东西是说，它的
对，放大一点的，应该是这个slide，是这个slide吗？不是，上次的slide，那我把上次的slide打开，顺便看一下。听不太懂 ，OK， 这样。
那我从这个开始。
哪一个？
从最基础
的。从最基础的。
对，就是它这个到底是什么意思？就是什么是这些要素？它到底是要做什么事情？
我可以，首先我一堆 quantum state 跟一堆 probability，数学上来讲很简单，总之我可以算出这个东西，就是我有一堆 quantum state， 他们是 vector 嘛，然后他们是 column vector， 然后写成这样的话就会变成一个 matrix 嘛。
对。
这是一个 outer product matrix， 然后我可以把这些 matrix 加起来，然后得到另外一个 matrix。对。那
它是要用来做什么？
它可以用来表示这个东西以一个更简洁，不太确定有没有更简洁，但某方面来讲更简洁的方法来表示这个东西。就是我有一堆 quantum state， 然后他们有 probability 嘛。我是等于是拿到了一个 random 的 quantum state 这样子，那我想说，那我有这个 random 的 quantum state， 那我去量它的话，例如说我去量它的话，我会得到什么样的 measurement outcome 这样子。
我觉得反正它是一团东西，然后就是我可以从里面得到很多其他的东西，这样的意思。
有点像，对吧？重点还是有这个 probability 啊，是 quantum state 加上 probability distribution 的时候，我要怎么描述它的？
对，问题是我在写作的时候有很多就是计算，就是说它到底是什么，它有些什么对 n 来讲，就是因为它给的 base 已经是一个就是 computational base， 所以它到底是对所有 base 一起计算，还是对某单一 base 计算，然后又可能有什么观测标、观测标之类的，就是因为。
对啊，为什么这个问题听起来有点奇怪？什么意思？
对，就是因为我主要问题是我看这个我其实本来看不懂，然后写作业的时候发现就是说， 我要用下面的公式计算，这边下面有些公式，对，像是像是这个东西，因为这个东西它的这个 I 是对每一个这个 measure 是每一个就是有可能的 state 去做计算。
等一下，你说的是哪一件事情
？measurement 就是 evolution， 我觉得我看起来像应该就是它会有一些，就它做一些 gate， 它就有点变化这样，所以我这个应该看得懂。就是 measurement， 主要是从 measurement 这边开始，就是它到底是想要说什么？这个是全部讲，所以就是它本身这件 image 就是一个叠加很多东西的东西，然后这个是对每一个有可能的几率做它的那个 measurement， 然后这个是把 measurement 所有东西加起来嘛。
我是不是应该把 density operator 当做是一个，就是把所有的 state 都混起来一起算的？
它是一个 state， 你可以把它看作一个 state 嘛，就是一个，其实你也可以把它想成就是 quantum state， 它是更加复杂的东西这样。
就它可以同时处理多个 state 这种感觉。
有点像，它是多个 state 的 classical mix， 或是。对啊，或者你可以直接把它想成它就是 quantum state 的。
所以这个 PM， 然后
就是更复杂的
quantum state， 其实是说就是我在对里面的每个 state 去做
但是应该不用去，等一下你在看的是 measurement， 我看一下是在哪？这里吗？这一页不是？
不是，
你看的是
最前面有这些公式的这一页，蛮前面一
堆。
我后面其实我在
这里 ，OK。
对，就是这边。
但是这里比较像是在推导，其实不需要看的东西，就是你真正想用的是你想要用的是这个结果。
对。你
想要用的是这个结果跟这个结果，其实都不需要这些 condition 的东西啊，就是真正好用的东西是只要看这个就好了。
哦。因为他前面就说那个 M of 那个 subscript M 这个东西到底是，因为作业其实出的是一个就是 computational base， 它不是一个就是合在一起那种，就是它不是一个 general base 这样。
什么意思？我有点忘记作业是哪一题？作业是
就是就是丢出一个作业，就是那个是塞一，然后是塞，然后我们要把它拿去做计算，就是单纯的计算题这样。对。
然后你说作业跟这个的差别是什么？
就是因为我想要用这个公式的时候，我发现就作业给是那个01的 base， 然后可是这边这个因为就是我感觉它到底是。
但01的比这个简单啊。这个是第一章的问题吧？是01的跟这个怎么合在一起的？这个你想要问的，我觉得是这个问题。就是因为我写的是最 general 的嘛，就是回到了我们有很多种不同 measurement 表示方法的。
所以我其实就是我说那应该就是根据这个，我就是直接照算这样。只是我就觉得说
搞不太清楚嘛。
对。
就01的你也可以写成这个 嘛，01的话就会是那个，你会是generalized measurement， 然后会说如果你是对吧？你要把 orthogonal basis 的 measurement 写成 generalized measurement 的话，基本上你是用这个公式这样，对吧？
对，然后再来就是我就看这些就是有点看不太懂，然后到底就是看他就是做很多其他的事情，然后反正最后我发现好像可以用对刚刚那个 general 就是，
因为我这里好像打错了，这里应该是我想要写的应该是 vi，OK。就往下课再改好了。这里先改一下好了。我想想看，我应该没有想错。measurement 跟什么？这里应该写 bi 比较好。
然后它就是那个
basis，OK，
那个就是关于 pure state 跟 mixed state，这到底物理意义是什么？就是我刚刚单看说，其实看他懂他想表达什么，就是 trace 等于一个最小的到底是什么？就是它实际上到底是怎样？因为我这样单看呢，我
pure state 就是正常框的 state 嘛，正常框的 state 就是 pure 这样子，然后 pure state 就是你可以把它写，然后它的好处是它可以写成就是一个 vector 嘛，就是我们一开始在讲 density matrix 之前的东西，所有都是 pure state 嘛，就是你可以写成一个 vector。那 mixed state 就是它其实他说我想象是我好多个 pure state mix 起来，就是我可能是1/3的几率是这个 state， 然后2/3几率是另外一个 state 之类的。那这样的东西我们发现需要用 density matrix 去描写它，那它就比较麻烦，它就叫 mixed state 这样子。
那这样跟 entangle 是什么关系
？entangle 是不同的事情。对 ，entangle 跟 pure 就是有点关系嘛，我们最后再讲，但是。其实是不同的概念，就只讲定义来讲 ，entangle 跟 pure 是不同的观念嘛。entangle 是说我有2个 system 的时候，然后我能不能写成这个 system 的东西，然后 tensor product 另外一个 system 的东西，对，这个是 entangle。然后
你看有物理意义之类的
吗？有啊，就是 entangle 会等于是说。例如说你在这个 system 做一些事情，做一个 state， 然后另一个 system 做一个 state， 然后一个 state。那如果他们都没有 interaction 的话，他们就不会 entangle。entangle 代表是他们是之间有 interact 过的才会变成 entangle state 这样。
然后就是 reduce density matrix 是。
但是然后我发现 entanglement 跟 reduce element 跟然后有没有 entangle 跟 mix 有没有关系？就是刚才讲的最后这里嘛。就是说，我们发现说，如果我的 two party 这个 pure state 的话，那这2个东西有没有 entangle 跟它的 reduced density matrix 有没有 mix 的是同一件事情，会是一样的。
伪知density matrix 是他在做的事情是有一致两性网织是一个 computation 事情，然后我想要，
然后我说我只看一个 part， 如果就是对我是一个 composite system， 然后它有一个在一起的 state 嘛，然后但是如果我没办法同时玩2个 system， 就2个 system 说不定也很远。就是我只看我这个 system 的话，那我会觉得我是一个怎样的 quantum state， 然后它会变成这个 reduced density matrix 这样子。
所以我的 reduced density matrix 是就是可以从看出它是看出它是一个独立的，还是一个就是 entangle 过，是这样的意思。
对啊。有点这种感觉。
看一下 purification， reduce density matrix。所以 purification 就是在对 reduce density matrix 做一些操作，让我们可以观察的一些结果。有人可以
是当掉了。Purification 不是物理上能够做的操作，是数学上我觉得我可以去算出一个 purification。
所以就是看这样图，就是不知道是什么 state， 可是 entangle pure state， 但是
OK， 我们可能先开始上课吗？
好，不好意思。
还是你要在课的，你可以再举手问一下，我会确定。
我有可能要想一下，因为
那你再想一下。
大概有点想法，但还要想。
OK。Okay, and let's go back. Seems like we have quite a few confusion density matrix, so maybe people can. Wait, let me try to find. So let's not on this one. Wait, where is my slide? Sorry. I got very confused. focus on my PowerPoint. Slide presentation. No, this is all slide. And where can I stop this? Yeah, my PowerPoint is stuck. Okay, that's annoying. And anyway, do people have a question on density matrix? It's I guess while I still so I should go. Wait, how do I? So it's asking me to save it. So if I go here, maybe this is save. Okay. Yeah. Anyway, let's try to have PowerPoint closed. No, not this thing. Yeah, it's there are a few confusion on density matrix, and so maybe let me stress once again. We want to do density matrix because we want to describe a probability mixture of quantum state. Okay. And yeah, so it's not quite possible with just the state vector notation we have. So let me try to pull out one of the slides we just not this one, sorry, one of the slides I just closed. So it's a density matrix slide. Okay, and the most important idea about density matrix is you want to describe this. Sorry, let me do this. Okay, so the whole idea of density matrix is we want to describe this ensemble of pure state. So we say we have. So before we have those pure state, those are quantum state. But then what if we have a probability mixture of quantum state? After all, in quantum mechanics, we got the probabilities all the time. When we do a measurement, we got some probability. Okay, so how do we describe a probability mixture of a quantum state? And that's where we get a density operator. We find out that, I guess the easiest way is you can just say, well, we have a different quantum state with different probability. And I guess that's workable, but it's less elegant. Okay? So you can have, you can say we are in, say, 0 state with probability 1/3, and we are in 1 state with probability 2/3, and etc. Then we can describe this ensemble pure state. But we find out that there is a nice mathematical structure that describes this thing in a more unified way. That is, you have those probabilities and vectors. Then you can just calculate this. Right now it's not reduced density matrix. It's just a density matrix. You can calculate this density matrix rho. Okay? And so it's this mathematical rule, and I guess everyone is very good at with calculation. So you can do this calculation, and you can get this density matrix. And we see that the density matrix totally describes the quantum mechanics that you can have on this ensemble of pure state. And one very important thing is that we see that a different ensemble will give us same density matrix. So yeah, so we have this one have 0, one have 1 ensemble, and one have plus, one have minus ensemble. And we see that they give us a same density matrix, and this means that whatever quantum operation you do on those two density matrix, you cannot tell them apart. And yeah. And so that's a density operator. The idea is that you have a probability mixture of quantum state. Then you can describe this probability mixture with just this density matrix here. And we have a whole bunch of proof, but I think we should jump ahead a little bit. So the only thing you want to do is that where are our postulates? Sorry. So we should go. Okay. So after this, okay, and so the calculation you really want to do on density operator are the postulates. Okay. And so if you evolve, if a system is in some density operator, then you evolve a system with U, then your system become a new density operator. It is a U row U dagger. And also, if you do measurement on your system, then then there will be different measurement outcome and different post-measurement state. Okay? And once again, we describe your measurement with those measurement operators. And I guess some of them with M and some of them with I, but this I should be M. Excuse me. So although I really like I, I'm not sure why I have small m here. Okay. Anyway, these are dominant indices. Okay, so if you describe your measurements with this set of big M's of small m, and then we can think about what are the outcome probability and the post-measurement state of your measurement. And basically, what you want to do is you want to calculate this m row and dagger. Okay, so you want to calculate this thing, and so the trace of this thing is your measurement probability. And if you normalize this thing with its trace, then it's your post-measurement outcome state. Okay, and so that's how you do measurement on density operator. Okay, and also then now here we have more confusing result here. It says that so we can kind of combine those two results together. And we ask what if we do measurement, but we forgot the measurement outcome. So we got the random measurement outcome. So then we can average together those random measurement outcome and get a new density matrix. And the new density matrix will be this sum and row dagger and row and m dagger. Okay. And are we more okay with this? And okay, so that's what you can do on density matrix. And now there is a kind of confusing thing about what the pure state and mixed state. Okay. And pure state means that pure state means that so now we say that everything can be written as a density matrix, and kind of go other way around. So we say whatever example you can write that as a density matrix. And then also whether your density matrix can be written as just one pure state, just one state. Okay, so it can be expressed as just an example of only one state here, only one state. Okay? And that will be pure state. And we really like pure state because if you are in pure state, then you can, instead of writing a matrix, you can just write this vector to describe your state. Okay? So that's pure state. And so pure state means that, so pure state for density matrix means that your density matrix can be written in this form. It's a projector onto some vector. And then for mixed state means that, well, you are not in pure state. It's you are probability mixture over something. Okay. With some non-trivial probabilities. Okay. So this is pure state and mixed state. And finally, then we go to the more confusing part. Then we go to reduced density matrix. Okay. Then we see that this density matrix expression is very nice because it comes very naturally when we describe a composite system. So we see that you have two systems A and B, and they might be entangled. So when they are entangled, then we see that we will want to describe A as a reduced density matrix. Okay. And then from something we just shown today, we see that if they are entangled, then A is not pure state. So you really need to describe A as a density matrix, and that's called reduced density matrix. And mathematically, so if you have any entangled, even mixed state, so you have an entangled state between A and B, so this is row AB, you can calculate the reduced density matrix on system A as is row A equal to trace B row AB. And so here I guess I should highlight. And so we have this equation. This is how you calculate reduced density matrix. But here I guess the definition is kind of empty because we have this trace B here, and we need to really define trace B. And trace B is defined. This partial trace is defined by those two properties. So if you have a tensor product with something on A and something on B, and then we'll basically trace all the B part. Okay, and okay, so the partial trace, and then you extend this by linearity to every matrix. Okay, and I guess here is a homework that we can do. So we can go to talk our TA that we can add this to homework. Check that those two equations those two properties are consistent. So we want to check that the first property is also satisfy linearity. Okay. Okay. Yeah. So this is reduced density matrix, and then finally we can go to the slide that we just end, the purification slide. Okay. Oh, let's try to. Sorry, I should save this. Oh, no. How do I close this now? Keep this and go to our purification slide, and yeah, go to the next slide. And yeah, and today we show even more connection between entanglement and being entangled and being mixed. Okay. And yeah, so the keyword is here. Oh, sorry. We're auto battery almost. Okay, and yeah, this is auto battery and faster than I think. Okay, and so this is a bit confusing. So being product state and being a pure state are actually different things, but they are connected in this picture. Okay, so here we have that. Okay, so this is quite confusing because I guess both product and the pure start with P, so you might think they are the same concept, but really they are totally different concepts, although they are related to this picture. Okay, so product is related, being a product state is related to being a pure state, and being an entangled state is related to being a mixed state, and how they are related is we think about this picture. So if we have entangled pure state on AR, okay, so I guess it's also important that this state is pure here. So this analysis only works if you have a pure state on this product on the whole composite system. So we think about we have a composite system that has two registers. So we have a register A, register R, and then you have a pure state between AR. And then you can calculate the reduced density matrix rho A of this total system or on this subsystem. And then there will be relationship between whether AR is a product state or entangled state, and whether rho A is a pure state or a mixed state. Yeah. And so we see that AR is a product state means that so AR is a product state means that AR is state AR equal to some psi A tensor some psi R. Okay, so it's some state on A tensor some state on R means it's a product state. Okay, and then rho A is a pure state means that rho A is just this psi A. Okay, so yeah, so it's very quickly you can show that if you are product state here, then you are a pure state here. Okay, because when you do partial trace on this thing, you will just trace all this R part, and you are left with this psi A. Okay, and I guess it's a bit confusing because when we say pure state, we either means the density matrix or the vector. Okay. Okay, and so this thing is about this rho A equal to psi A psi A. So maybe this is a bit of a source of a confusion because we call a pure state we call either density matrix pure state or we call the state vector pure state. Okay, so it's a bit of a confusing notation, but yeah, this is what the people do all the time. Okay. So this is a bad notation, but people do this. Okay, so we say rho is a pure state means that it can be written as a projector onto this vector, and this vector we also call it a pure state. Okay, so we see that when we trace out AR, I guess technically you should trace all the density matrix related to AR. then you will get this density matrix row A here. And yeah, but people also get lazy, says that you have this pure state, and your trace out becomes this pure state. Okay. Yeah, so that's between product state and pure state. And then this otherwise is just when you cannot in this form, then you cannot in this form. So you have an entangled state means that, well, in streaming decomposition means that you have more than one streaming coefficient. So you have psi A tensor psi R plus something. And that means that your row A can also cannot be written in this projector of just one thing. You will be written as different summing over different pi here. Okay, I guess here we have a more general form. We have AR equal to this thing, and yeah, we have AR equal to this thing, some I square root of pi IAR, and the row A is the some I pi IAIA. Okay, and yeah, hopefully this, and let's try to write something, a little more thing to, let me see, where should I write? Maybe, okay, it's empty here. Okay, so maybe a bit of, okay, I really want to write here. A bit of thing to make things a bit clear. So when we talk about reduced density matrix, we start with a density matrix on AR. So let's write this row AR here. And so row AR equal to this AR thing. And it will be equal to some IJ and a lot of things, square root of PI, PJ. And IA, IR, and JA, JR. Okay. And actually, we have written this before, and it's this thing here. Yeah, this thing is row AR, and it's a quite complicated thing. So this thing here, this is row AR, and yeah, just here you already see that we are not consistent with the notation we said before. So here we are marking a subsystem as a subscript instead of a superscript from the previous slide. But yeah, hopefully this is not too confusing. Okay. Yeah, because from the previous slide we say we mark a subsystem on the uppercase here, but here we do lowercase. Okay. And I guess, yeah, so to be a bit more consistent with the notation, let's also write this row AR as a subscript, because why not? Row AR. And row AR is this thing. Okay. Okay. Yeah. So hopefully this makes the story on density matrices a bit more clear to you. And yeah, I guess one thing to note again, being product state and pure state are totally different ideas, although they are related in this way, in this partial trace and purification picture. But technically, they are very different property. A product state is a property that you talk about on a composite system. You are saying if a system has multiple parts and your state is a state on one system tensor another state on another system, then you are in a product state. And pure state means that if you are writing if your density matrix of your system is can be written I should say is correspond to just a K vector. If your density matrix is if your density matrix is just a projector one to one vector here, and then your state can be just described by this one vector. Okay. Hopefully this makes things clear. Okay, yeah, and I guess later on we can have more questions. Yeah, please come to me if you have more questions here. And for now, let's start next section. And let's change the slide again. We'll change a lot of slide. And yeah, let's go to totally different word. Let's go to not quantum, so we will forget quantum for now, and let's talk about classical computation. So this is for those of you which don't have such strong computer science background. Okay, so let's also review some classical computation, and hopefully those will be reviewed. We are following a textbook, and yeah, this is about chapter 3. If you want more detail, look at chapter 3. I think we actually omit a lot of this section because we don't use too deep of classical computation here. But anyway, let's start with very theoretical computation, and we start with this Turing machine. Oh, question? 这个应该在网PPT， 这个应该有 po， 昨天好像有 po 上去。应该在课程。我可能命名错了，应该写，但是它的确是 CH3，但是应该是 classical computation 的。CH3 是我们有那个scope PPT 是我们现在这个东西，然后 CH3 是我们其实是有课本的，我们有 Nielsen 创这本课本，然后你去看它第3章。就会是我们的 PPT 里面内容，就是你可能要购买课本，或者是用其他方法得到课本的档案，然后对你去看课本的内文的话，它的第3章是这个内容，OK， so this is actually on textbook, and you look on textbook, you have more detailed explanation of everything. Okay, so let's start with a very theoretical description of computer science. So how does computer scientists, I guess the theoretical computer scientists calculate things? Is they like to start with this weird Turing machine. Okay, so Turing machine named after Alan Turing is a very nice theoretical construction of computation. It's nice because it's simple and it technically can calculate almost everything. And anyway, so Turing machine is this basic model of computation. And I guess let's show a picture first. So it has this really weird machine. So you have a kind of a processor part of the machine, and they have some program, finite state control. And so this is kind of like the is the program, and you have some internal memory of your CPU, and then there is a really long disk here. It has a tape. You can write 0 or 1 on your tape, and then you can read from the tape, or you can write on the tape. So basically, the Turing machine. And the important part of a Turing machine, I guess, is that the tape is infinitely long. So this is very nice because this is a machine that can calculate a function of any size. So you can have infinitely long input and infinitely long output because tape is assumed to be infinitely long. Okay. And theoretical computer scientists come up with a lot of things in Turing machine. Okay. I guess here we have a very just a very basic description over here. Okay. And so there is a program. As we said, the program will decide what the machine does on each step. And there is some finite state control. So that means that you have some finite number of states here. So maybe 0, 1, 2, 3, 5, 3, 2, 1, 2, 3, 4. And the program will think whether it's in different state and will do different things. Okay. And as we said, the tape is kind of like the memory of your computer is infinitely long. Okay. And and then there's a read-write tape head, and so the head is a funny thing here. So you can read and write on the tape, and also in the usual construction of Turing machine, we assume this tape has a very limited movement. So the head can only move to left left is this direction. I guess left is different direction for you. So left is this direction for you. So you can only move left or right in each step. Okay. And yeah, so people calculate how many steps can your Turing machine compute your algorithm, etc. Compute your problem, etc. Okay. And it turns out that I guess here we are missing a bit too much. But it turns out that Turing machine is very powerful. So people like this because it's simple and also because it's very powerful. So that's quotation powerful. So basically everything computable can be computed. So actually I guess that's a quotation mark, computable function can be done on Turing machine. Okay. And yeah. Okay, so it's very nice. So every computable function can be done on Turing machine, and I think actually it's not too slow to a computer scientist. So to compute things on Turing machine usually only slows down polynomially. Where what do we mean by polynomially? We will talk more detail in later part of this slide. Okay, so it's very simple because it's just this thing, and so for every algorithm you can just have your Turing machine look at this. You just change the finite state control in the program, and you can calculate everything that you can calculate. Okay. And I guess something that's in textbook, but we omit here is that. So this is a very theoretical. This is a very theoretical construction, and what people actually study with Turing machine a lot is there are actually things that you cannot compute. There is this uncomputable function in the world. Okay, uncomputable function. There are uncomputable function. And it's nice to know they exist, but we will not spend time into detail here. But it's described in a lot of detail in the textbook. And yeah, you control that function as kind of a paradoxical function. So this so-called halting problem is uncomputable. And I guess I can describe in words here. So halting problem asks you that if you give me an arbitrary Turing machine, can I determine whether the Turing machine halt? Okay, so I guess I need to say a little more about things here. So you have a Turing machine is this thing you will run on program, and the Turing machine will either just run forever or you will stop and say they give you the answer. Okay. Because things here is I guess different. Okay, so because the Turing machine it has a whole bunch of program inside, and you can think about if you design your Turing machine not so nicely, then you can contain some infinite loop inside, and the thing will run forever and it will not halt. Okay, and the halting problem just asks you that can you decide that every Turing machine will halt or not? Okay. And turns out that a very hard problem is you can prove that it's uncomputable. You cannot use a Turing machine to decide this problem. Okay, so there are uncomputable problem, and that's a halting problem. And yeah, so it's a very nice topic on theoretical computer science. And you want more detail, you can read the textbook. Okay. So yeah, this is our very first description of a Turing machine. Okay. And yeah, this is a very theoretical model of computation. And now let's go to a more physical model of computation. This is more like how we actually build on computer. So that's the second model. Okay. So yeah, as we said, Turing machine is very powerful. It's equivalent to Turing machine in computational power. And but the second model is much more straightforward to think about, and so it's more convenient and realistic. Okay, And so for the circuit model, we think our computation is done by this circuit. And the circuit is composed of wires and gate. So wires will pass your information around, and we're talking about classical information. So each wire will just pass 1 bit of data. So wire will pass 0 or 1 along it. Okay, and then there are gate that will perform computational tests. Okay, and so we think about. I guess this is also a bit abstract. So we think about this quite physical, although in actual devices this might not be how you actually perform things. Okay, so we think about those wires are just like a physical copper wire that can pass your data. So we will say signals that are either 0 or 1 throughout the wire, and so we will send a signal from this input side, and the signal will pass through the wire. And okay, now this gets a bit on physical. So this wire we think is kind of like physical wire, but also represent time. So we think the signal will just pass through in sync. So we think there are a whole bunch of information. So we can kind of think the input is here, then you have a whole bunch of information. Send it here, and then they will. A whole bunch of information set in here, and then they will pass in, and just step by step with same kind of the same height at the same time, and then we will hit those blocks that are called gate, and the gate will change the signal in your wire. So you have some input, and then you will have some output that might be different from your input. And here you see that gate might act on 1 or 2 or many wires. Okay. So you can have a gate that acts on many wires, and so the output of those 2 wires will depend on input of those 2 wires, etc. And yeah, so you have information set in here, and they go through several gates, and whenever it goes through a gate, you will change your information, and yeah, then your output of the wires, and that will be the outcome of your computation. Okay. And yeah, and so basically this how you place your gates and wires together will become your algorithm. Will be how you calculate something. This thing will determine input and the output pair. So you have some input, you will get some output from here. Okay, and yeah, so here are some hopefully review of some gates. And I guess we will actually not draw those symbols, but it's still nice to know these symbols. Okay, so those are some example gates that you can have in your circuit. So maybe there is a NOT gate. So your input is A, then output is not A. Means that if input is 0, then output is 1, and the input is 1, output is 0, etc. So we'll flip the input. And there are AND gates, so you'll calculate the end of the input. And so this means that the output is 1, if only if both the inputs are 1. And you can also have OR gate. Means the output is 0 if only if both inputs are 0. And yeah, you can have XOR gate. And XOR gate is basically addition mod 2. Okay, so this thing means A plus B mod 2. Means that this is 1 if only if A not equal to B, and 0 if only if A equal to B. And XOR is actually a bit more important, so let's yeah, describe this a bit more. Okay, actually that's why I actually write it down. Okay. And yeah, we like XOR. And there are NAND gate and NOR gate, so they are just basically just AND gate then with a NOT, then the OR gate with a NOT. So flip the AND gate and flip the NOT gate. Okay. And so those are some basic gates, and 2 things that are a bit of a special rule here is that we don't allow feedback loop in our circuit. I guess if you actually build a physical system, you can kind of always build a feedback loop. But in our circuit construction, we just don't allow this to make our logic flow more consistent. So our logic flow is you just have data inside, and you can just calculate it through time, and do one gate, get one by one, and calculate the output. Okay. And also, only in classical computation here we allow fan out, so we can have this kind of gate. So we can guess technically fan out is a gate, but we just draw it as a wire that's split into 2 or more wires. Okay, so if the input is 0 here, then you do the fan out gate, it will split into 2 0. Then if it's 1 here, then it will split into 2 1. Okay, etc. So fan out gate is allowed, and so a bit of spoiler, this will not be allowed in quantum circuit because quantum we have no cloning, so we cannot have a psi inside and a ket psi inside and 2 ket psi as output. And yeah, so in quantum circuit there is no fan out, but in classical we can copy our 0 1 data, so we allow fan out. Okay. And yeah, a circuit model usually what we calculate is so-called because a lot of time we calculate is so-called Boolean function. Okay, and Boolean function is so it has a cool name, but it's really a simple property. It's just a function with okay. So Boolean function is a nice name to remember. It's a function that has one put. I guess it's a discrete function. So in this course, information are usually discrete. So we think about discrete function, and it has some n bit as input, and so the Boolean part is the output is only 1 bit. So yeah, Boolean means 1 bit. So you have n bit input, n can be whatever thing, but you only have 1 bit. So 1 bit output is 0 or 1. Okay. And we think, as we say, every information is discrete here. So any function is just n bit input string to n bit output string. And so Boolean function is nice because we can think any function as just m different Boolean functions. Okay, so you can say each output bit here is 1 Boolean function. So if you just calculate, you want to calculate any function, you can just calculate m different Boolean function. Okay. And so that's Boolean function, and then we get another important concept here is this universal gate set. Okay, so now I can describe what's a universal gate set. Universal gate set is a set of gates that you can use it to construct any Boolean function. Okay, so as we say, if we want to do an algorithm or excuse me, want to do any algorithm or any function, then you can piece together your gates and the wires. Okay, and universal gate set is a set of gates that can, if you only use them, you can get any Boolean function with by putting together those gates and some wires. Some maybe something like this. Okay, and yeah, so that's the idea of a universal gate set. And just as we said before, we can specify any algorithm by saying, so in circuit model, we specify algorithm by just describing how you connect the gates from a universal gate set. Okay. And yeah, later on, I guess we can say a little more. So later on, we will describe quantum universal gate set, and yeah, so it's a nice idea that we'll visit again in quantum world. And in terms of classical universal gate set, I think if you go to theory course, those two are the most important, most famous universal gate set. And so one of them is only NAND, and another one is AND gate and NOT gate. Okay. And this NAND is nice because it's a gate set with only one gate. Okay. Yeah, so that's a universal gate set. And I think, okay, I will check this later, but I think you probably also need fan out here. So this is a little different from quantum, because quantum don't have fan out. But I think also you want this gate set with fan out, then you can construct any function. I need to check this. little more. Okay. Yeah. And that's a universal. And so this is circuit model. We describe our algorithm by putting together a whole bunch of gates with wires. And you see that we have this contraction. This construction, you can put some input here, and we get one wire out and one wire as our output. Okay. And now let's talk something that we'll use a bit more. That's a sympathetic notation. And we only have 10 minutes, so I guess let's only do a very quick review, quick overview here. So sympathetic notation is something we do a lot in theoretical computer science. Is we want to study how fast something scales. Okay. Okay. And so this is really describing, I guess, describing functions. Okay. So maybe think about, I guess, here. Yeah. I guess here we have another word, but let's think about this function here. So we have a function of n here, 24n plus 2 log n plus 16. And as we say in a sympathetic notation, we only care about how this thing scales when n goes to infinity, when n is very large. And when n is very large, we know that, so if you remember from calculus, we know this linear function, this 24n, grows much faster than log n. Because in calculus, you can show that this n is much larger than log n when n goes to infinity. Okay. And so sympathetic notation kind of want to say we look at this thing and we don't care, because we only care about what happens when n is very big. Then we don't care about the log n part, and we don't care about the 16 part. We need to care about the 24n part. And actually, we don't even care about 24. Okay, so now we get very theoretical, because in practice, you probably care about 24 factor in your performance, but we are not going for theoretical. We don't even care about this 24, and we only care about this n here. Okay, and so this is the idea of sympathetic notation. We want to say this thing is order n. Okay, and so this is a big O notation. Okay, and so now this is a bit confusing. So this big O notation. I guess when you are not very strict, people will write big O notation for everything. Okay, and they will say this thing. They will say this thing is order n, which is technically true. But there are a lot of things on this big O notation. So if we go to big O notation, and we go to technical detail later. But for now, one thing to know is that so there are a whole family of big O notation, and in particular, so technically in computer science, big O only means upper bound on your function. Okay, so big O notation. So say we say something is your function f of n is a big O of say n, then that only means that your function is upper bound by n when n go to infinity. And and they are related to notion, this big omega and big theta. So big omega means lower bound. So we say so f of n is omega of some g of n, means that when n goes to infinity, f of n is greater or equal to your g of n. Okay. And then there's this big theta notation, which is actually probably you mean when you write the big O notation. Means that you have both big O and a big omega. So when n goes to infinity, your f of n is about equal to your g of n, and up to some constant range. Okay, and so this thing will say this is order n. Okay, and so people will say this thing is order n. And but technically, you probably means this is theta n. Okay, so when n goes to infinity, this is some constant factor to n. Okay, and And so here we have technical detail of this asymptotic notation. And there are actually two more notations here. So there are also small n and small omega. We have a typo here. This should be small omega. Okay, small omega. We also have a small notation and a small omega notation, means that this is less or bigger instead of strictly. This is strictly less or strictly greater when n go to infinity. Okay, and anyway, we'll go to more detail in the example later on. But here we just show you, some quick overview of this asymptotic notation. And we'll describe a lot of concepts with them, and so this is an important thing to actually know how to calculate and know how they are defined. Okay, so we'll continue on next Tuesday on this asymptotic notation. Okay, so see you on next Tuesday.